Okay, let's get started. Please turn on your video if you're comfortable with it, otherwise get ready with the icons. So we were talking about representation. Of functions as a power series. And we were using this basic identity we know in geometric series to try and get some representation of some sort of non-trivial class of functions as an introduction to understanding how we represent functions as power series and what benefit we get from that. So we did that example. We did this. We found that we can represent 1 over x squared as the sum k equals 0 to infinity minus 1 to the k, x to the 2k, I believe. Yep. Right, and how did we do this? We just thought of this 1 over 1 plus x squared as 1 minus x squared, and then wrote out the power series expansion for minus x squared, and it exactly became this with some algebra, right? And use star, and we use this thing, star, right here. And then we will learn some more general things. So look at this. I claim that we can represent this also as a power series. How would we do this? Use a similar idea. We have to use this identity somehow. How do you see that we can do this? Yeah, well, let's factor 2 from the bottom. So then we're going to have 1 plus x over 2, which looks more like this, but not quite like it, right? But we can also just do this. Actually, let's pull out the 1 over 2, just straight up from the thing. Like this, yeah? And then we do the same trick. So hopefully you're going to get comfortable with just directly putting this expression inside this. But if you're in any doubt, just call it something else. So let y equals minus x over 2. Then what we have is 1 over 2. 1 over 1 minus y, and then we use this basic formula, k equals 0 to infinity y to the k, and then put back what k actually is. All right, and then we can clean this up a little bit. Let's take out the minus 1 from this expression, so we have minus 1 to the k, right, pulling out the minus 1, and then we're going to have x over 2 to the k like this, but we have this 1 over 2 right here, so ultimately we can write this like this, k equals 0 to infinity, minus 1 to the k, x to the k over 2k plus 1, where I've taken this 1 over 2 and I've multiplied it through so that it comes down here. Yeah? And what we're looking at is exactly now a power series. We're looking exactly at a power series. Our coefficients in front are these guys right here. Okay, good. So with some functions which have some kind of structure we see that is somehow translatable into this form, we can just use this basic expression to get a power series expansion. Yeah? Yeah? But we're not done because we want to discuss what is the interval of convergence of this expression here. Yeah? What is the interval of convergence? Firstly, what's the radius of convergence? What restrictions on x do we need to allow us to do this argument here, this sequence of steps here? Well, let's check. So let's see where we use assumptions about x. So this is just algebra, right? Here we're not doing anything. Yeah. This part right here, we're just calling it something else. This step, when we do this step, we are actually using stuff to do with y and therefore to do with x. Yeah? Because this step right here is only valid if the absolute value of y is less than 1. Yeah? So this part, let me put this in little, needs mod y less than 1. Yeah? But once we have this, then this thing is just algebra again. So whenever the series actually converges, when it makes sense, such as it would do when mod y is less than 1, then everything which algebraically I'd like to do with the series we can do just as easily as we can do if it's a polynomial. So where they converge, series are a completely nice object. So this is nothing. We've just rewritten what y is. This is algebra. This is algebra. All these parts here, completely standard algebra. Yeah? So the only point in this sequence of steps where we needed anything was here. Because this is our basic representation that we're using to start to write things as a power series. Yeah? So, since this is only true, that's the same as saying that x squared over 2 is less than 1, which is the same as saying mod x is less than 2. Yeah? So let's draw a picture. The series is centered around 0, right? So we are here, and this is what we have, right? We have this. So the series converges anything strictly between 2 and minus 2, so the radius of convergence is 2. Okay. All right. Have we answered our question? Do we have everything now? Do we know everything? Indeed not. So what was our question? Our question was, what was the interval of convergence? What we have is a power series radius of convergence, which tells us that everything strictly between minus 2 and 2 is good. Everything which is strictly outside doesn't converge. But how do we determine the entire story? How do we determine exactly all the x for which this converge with no exceptions? What do we do now? And we need to test the endpoints. The only thing unknown at this point is this, right? So unknown at this point. And once we know these, we absolutely know everything, right? So to find the IFC, interval of convergence, check x is equal to minus 2. So we put in x equals minus 2 into this expression. What do you think? Will this thing converge? Thumbs up if yes. Thumbs down if no. Everybody take part. I need to know what you're thinking. Excellent. Someone who hasn't spoken yet, give me a reason why. Yes, so when you put this into this expression, our series is, so the series is this, but let's go back one step until we see this. And what do we have? We have some k equals 1 to this, 1 over 2, and then we have minus 1 to the k, and then we're going to have minus 2 over 2 to the k. So this part indeed is the same as minus 1 to the k. Oops, have I dropped? This is the k right here. So this is the same as minus 1 to the k. Go to space. So it is indeed flipping between minus 1 and 1, but when we multiply these two guys together, actually the series just becomes this. Just 1. Right? We're just adding 1 forever. But at this point, we're perfectly convinced it doesn't converge because by the divergence test, these terms are not going down to 0. There's no possible way these things can converge. Right? So it does not converge. What about the other endpoint? Thumbs up if you think it converges, thumbs down if you think not. Okay, great. Someone else still, give me a reason. This exact same reason, indeed. Yeah, if we just plug in 2 into this, now we're just going to have 1 to the k, which is just 1. So the only thing we're summing is minus 1 to the k. Again, it just doesn't go down to 0, doesn't converge. This expression has no meaning. Yeah. So does not converge to. By the divergence test. So now we know everything. And in your web assign, you'll see there's quite a number of expressions that one way or the other we can turn into something like this and then extract the power series. And then being a bit careful about what assumption which we use when we do this, we extract off what is the radius of convergence. And even more, we can work out the interval of convergence pretty easily. Okay, so that's the first thing you're going to learn or going to need to be able to do for this series is power series expand, things like this. And at this moment, the only thing we've told you about how to find a power series expansion is this trick. What about when you see something like this? Can we power series expand this guy? What do you think? Can we do this guy? Thumbs up if you think we can, thumbs down if you think we can't. Okay, indeed, we can do it. So, how? How? So this is a lot like the previous guy, right? So, yeah? That's a hint. So how can we do a power series expansion? Oops, I wrote this wrong. This is 2. Okay, go ahead. X to the power 3, yes. Yeah, we could do the same thing again because this thing we can put into this form of a power series, but we actually already know what the thing is, right? So we actually know that this thing is the sum k is equal to 0 to infinity 2 to 1 to the k over 2 to the k plus 1 x to the 2k. This is what we already learned, right? So we can just go directly from this thing, putting this into star, because in its interval of convergence, the power series is just as nice as a polynomial. If this is a polynomial and we're multiplying it by x to the 3, you would just multiply each term, right? The same thing is true so long as we're inside the interval of convergence. So into star, we have that x to the power 3 over x plus 2 is what happens when we just multiply x to the 3 throughout this entire thing. And then it's the sum k equals 0 to infinity minus 1 to the k over 2 to the k plus 1, x to the 2k plus 3, like this. Yeah? Everybody okay with this? This makes sense to you? Thumbs up if so. Thumbs down if anything's unclear. Or put it in the chat and someone can ask. Okay, good. Good. Just remember that it's just an as polynomials. If I just had k equals 0 to anything, to 100, and we had something like that, and we want to multiply it by x to the power 3, then you'd have no issue. You'd know exactly. You just multiply it through. And the same thing is true for a series, so long as you are within the radius of convergence, right? And again, the reason this thing works is because we use this power series expansion when the absolute value of what we called y, which was x over 2, is less than 1. So this thing holds true for mod x is less than 2, you know? And if we think a bit more about it, it's actually going to have exactly the same radius, interval of convergence, because the first part of it won't converge unless we are strictly within 2 of 0. In other words, if this is actually true, there's no endpoints that work here, right? So we can find the radius of convergence, and we can also find the interval of convergence in exactly the same way as we did before, or just using the fact that we know the interval of convergence of this thing. Oops, minus 2 to 2. Yeah? So sometimes there's expressions like this that we can still turn into something that we can get from algebra. But now we're going to talk about differentiation and integration of power series. Okay, given a power series, let's put it in its most general form. Actually, let me call it f of x, because it's a function. Once we put it in its general form, so let's write f of x is the sum k equals 0 to infinity ck x minus a to the k. So this is the most general form of a power series. All right? And it's going to have its interval of convergence. That might just be the single point a, or it might be the entire real line, but there'll be something, right? We can start by saying the function f is differentiable. And the derivative, you can just write it f prime of x is given by, so if we differentiate this expression, the k equals 0 term is just, it's just c0 x minus a to the 0, which is just a constant term, right? So that thing just vanishes. So let's write out the first few terms just to clarify. So when k equals 0, we have this. K equals 1, we have this. When k equals 2, we have this. And then so on to infinity, right? So when we differentiate something like this, then this first c0 term will just vanish. You know, so it's not there. So we start our index when k equals 1. And then we go to ck. And if we differentiate this term, I mean, it's just going to be 1, right? We can differentiate x minus a. That's a trivial thing. If we differentiate x minus a squared, it's just going to be 2x minus a. Yeah? If we differentiate the next guy, which will be x minus a to the 3, it becomes 3x minus a squared. Yeah? So we're differentiating this thing term by term exactly as if it was a polynomial. So what would we get? We'd get k x minus a to the k minus 1. Right? So the first term would be c1, the next term would be 2, c2, x minus a squared. The next term would be 3, c3, x minus a to the power 3, and so on. Right? Exactly what would happen if we differentiated this expression term by term is what we would get. as the derivative. Exactly what would happen is if this was a polynomial. Yeah? So this is the first part of the theorem, that given a power series, we can actually differentiate it so long as we are within the radius of convergence. Yeah? So for mod x minus a less than r, i.e. within the radius of convergence. And that's the first true fact you need to know. Is the statement clear? Is this meaningful to you? Yeah? All right, let me state the second part. And we can integrate. And the antiderivative is what would happen if we integrated this expression term by term. Sorry, this expression term by term. Yeah? So if we integrated just the constant c0, that would just be c0 times x plus a constant c, right? Integrated this thing, it would be c1 x minus a squared over 2. Yeah? Antiderivative of this guy will be c2 x minus a to the power 3 over 3. So I'm ignoring the constant now because we already added it. Yeah? So this thing is, I'm going to put the constant c at the end. So it's going to be, I'll write it in the general expression and then I'll write out the terms one by one. So we go, the sum k equals 0 to infinity. Right? So this is the general expression, and we take the antiderivative of each term inside this. So we're going to have ck x minus a to the k plus 1 over k plus 1, right? And this is the antiderivative of this thing right here. And then we're going to have plus constant c. Okay? So look at this. This thing is the antiderivative of this thing. Are you with me here? Yeah? This is not a mysterious, surprising thing, what I'm doing. This is really what you'd expect if the world of math was very nice to you. You'd expect this to be true, right? And then just writing out the first terms just to solidify it in our minds. So this thing becomes c0 to the x. This thing is c1 x minus a squared over 2. This thing is c2 x minus a to the power 3 over 3. And so on, so on, so on. And there is a constant c at the end. Yeah? So when I was advertising this section to you, when I said one of the powers, one of the powerful consequences we get of being able to write things as a power series is that it becomes now trivial to either integrate or differentiate them. And this is this theorem, that once we have them power series, then differentiation is just differentiation of term by term, exactly like a polynomial. It's exactly as easy as differentiating a polynomial for that reason. And integration is integrating term by term exactly like a polynomial. Yeah? And integrating or differentiating polynomials, as you know, is just completely trivial, right? Nothing hard there. Yeah? And this is what we have. This is what we have. This is one of the big payoffs. And again, it holds true for x within the radius of convergence, which I should state explicitly, where R is the R of C. So my two halves of the theorem somehow spread out a little bit. Yeah. So this is the first half up to here. Differentiation. The second half is that we can integrate. Cool. All right. So that, as you're going to see, is going to give us many powerful consequences. But we're going to start with just using this to represent a wider class of functions. Because once we have a function that we can either integrate or differentiate to turn it into this algebraic form 1 over 1 minus x, then we can put it as a power series, and then we can go backwards to get back to where we started. So if we have a function which we have to differentiate to get it into the form of 1 over 1 minus x after some algebra, then we expand it, and then we integrate to get back to where we started from. And integrating a power series still gives us a power series, and the power series still has radius of convergence, whatever the one we had before was. So doing this does not change the radius of convergence. This radius of convergence is the same, right? So maybe like I'll emphasize this too. Very weird splaying out of information here. And note the R of C of these power series, the derivative and the antiderivative, is still R. So we don't have to worry about finding the new radius of convergence. It's still R. It's exactly the same thing. Okay. So once you're within the power radius of convergence of your power series, you stay in that world. Everything is good. Nothing goes wrong for you. You differentiate. You have another power series with the same radius of convergence. You integrate. Another power series with the same radius of convergence. Okay. So is the statement clear? First of all, before I erase it, thumbs up if the statement's clear to you. And now we're going to start to use it. And this gets a little bit harder. Not too hard, but it's a little bit harder. So we have to keep our widths. Example 5. Express as a power series okay, solution. This is not the right expression. This is this expression. Okay, so express 1 over 1 plus x squared is a power series. All right, so there's no algebra to turn this in the form of 1 over 1 minus x, right? You can mess around with this as much as you like. It's just not going to be in that form. Well, it's not going to be in that form in any useful way. I mean, you could expand this out. You're going to have 1 plus 2x plus x squared. Then maybe you think, oh, I'm going to let y be minus 2x minus x squared. But then try and write that out. It becomes an awful mess. You might succeed, but that'll be the hard way to do it. So we're going to use what we did before, right? Sorry, we're going to use what we just learned. Yeah? And what did we just learn? We just learned that if we have a function, that we can express as a power series, then we can integrate or differentiate it and still have a power series. Yeah? So as this guy is written, there's no obvious way to put it in this form of 1 over 1 minus y and get something useful out of it. Yeah? But we can change the game because we know we have the right to integrate and differentiate our power series as we like, just easily. Yeah? So if we can't actually represent this guy in the form of 1 over 1 minus y and then put in a power series, then we're still in good shape if we can either represent the antiderivative or the derivative. Because if we could represent either the antiderivative or derivative, put it in a power series, then we can go back. We can go back. Yeah? So we have our original problem right here. Can't see a way to do it with just some algebra. We can either shift it to the left or to my right by differentiating it, or we can shift it to the left by integrating it. And now we have these two different functions. And if either of those can be put into the algebra that we want, we're all good. Because then we can just go back. Whatever we did, we can go back. All right, so look at this. Is there some guy we can find which is either the antiderivative or derivative, which is going to be useful for us here? Obviously, yes, otherwise it wouldn't be here. But tell me which one. What do we want to do with this thing? Do we want to take the antiderivative or do we want to differentiate it? Indeed, yeah. So notice that if we differentiate minus 1 over 1 plus x, we differentiate this guy, right? That's the same as minus 1 x plus 1 to the minus 1, then I should actually write this as a differentiation. Let me do that as a sentence. If we take the derivative of this thing, then it exactly becomes the thing we're looking for by the chain rule, yeah? Or by the power rule. So this is x plus 1 to the minus 1. We differentiate it. So the minus 1 comes down, kills this, minus 1 becomes positive, and we have 1 plus x to the minus 2, which is this. Yeah? So the antiderivative, sorry, when we differentiate this thing, we get this thing. So the antiderivative of this guy is this guy. Which is indeed of this algebraic form. So we're going to write this as minus 1 over 1 minus x, like this. And then this thing, the power series expand. I'm going to do this in one step. I'm not going to write the y now because we know what we're doing. Right? So k equals 0. And then it is this thing minus x to the k. Then we write out what this is. This is minus 1, k equals 0 to infinity, minus 1 to the k, x to the k, and if let's put the minus 1 through and just have a neat expression like this. K equals 0, minus 1 to the k plus 1, x to the k, and when is this going to converge? We use this step right here, which requires that absolute value of minus x, which is the same as absolute value of x, is less than 1. Yeah? So we have the power series expansion of the antiderivative. Yeah? Cool. But we can go back now. We can go back. Yeah? So d by dx of this guy is the thing we want. So d by dx of this guy is this power series. And we can differentiate it term by term, right? So forget that this is sum from k equals 0 to infinity. Just think of it as a polynomial, and then this is trivial to differentiate, right? So k equals 0 to infinity. So when k equals 0, we're just going to have x to the 0, so that term actually won't be there, so let's just get rid of it, right? Oh, I should have added a constant term here, but that will also... Okay. So we have a constant term here, but the antiderivative in its general form is this thing plus constant c right here, which I didn't write, but it doesn't matter because we're going to go backwards, but I want to not completely skip over this point. We also get a constant term from the k equals 0. As you know, antiderivatives are just defined up to their constant term. So when we do this procedure of taking the antiderivative, then going back, the constant term is going to vanish because we're going to integrate and differentiate again. But let's be careful, because it's not always going to be the case that we can just forget about the constant term when we take the antiderivative of a power series. Okay, we are back. So this is our expression. We have the k equals 0 term, which is the constant term. It vanishes. The plus c also vanishes. So we just start from k equals 1 right here. Start from k equals 1, right? And then we're differentiating this thing. So we have minus 1 to the k plus 1, and then we're going to have x to the k minus 1, just like this. Yeah? So the derivative of this thing is this thing, and the derivative of the same thing is this thing. So what we've said is that this thing is equal to this thing. Yeah? This thing is equal to this thing. Okay, so let's write that as a sentence, i.e. 1 over 1 plus x squared is this guy. And the radius of convergence is the same as the radius of convergence of the thing that we had before, the original power series, right? Which is happening when absolute value of x is less than 1. All right, let's recap the steps. So we have this guy. We can't turn it into any algebra that we can use, you know? But we can take the antiderivative. Okay, let's do it like this. Let's put a kind of pictorial pictorial narrative of what we did. So we had this guy, can't do anything, so we integrated. Yeah? And then we get this guy. Whoops. And then this thing we can put as a power series expansion, right? So then power series, which was this expression right here. K equals 0, infinity, minus 1 to the k plus 1, x to the k, and plus constant c. Yeah? And then once we have a power series, we can differentiate to get back to where we were before, representing this initial function. And when we differentiate it, we get this expression, k equals 1 to infinity, minus 1 to the k plus 1, k x to the k minus 1, and the constant vanishes, of course. Okay, so we had something, we integrate, we do the power series expansion, we differentiate. Yeah? So once again, we start, we put it into a different world by integrating it, finding the antiderivative. Now we can do a power series expansion, now we differentiate it, get back. All right. Is everybody happy? Yeah, it's a little bit harder. It's a little bit harder, but it isn't that hard. So I wrote up the steps somewhat carefully. If I was doing this on my own, what would I do? I would just write this identity like this, and then I would just replace what's inside here by the power series and differentiate it through. So if I was doing this on my own, I would just write it like this. I would say, okay, I know what this is. This is the derivative of minus 1 over 1 plus x. And I know what that stuff is. I can power series expand it. K equals 0 to infinity minus 1 to the k plus 1, x to the k. Yeah, and then I'm just going to differentiate through. So when if you write it in this way, it's actually just one line. So this is the kind of slick, fast way to do it. And that's it. That's exactly what we had before. Yeah. All right, so I must be out of time. So everybody who wants to leave. I'd like to do at least one more example of this, try and solidify this. All right, before I erase the board, everybody happy? Everybody okay? Yeah, there's a lot of stuff I want to cover. All right, maybe I just do one then. What about this? Find power series of this expression here, log of 1 plus x. All right, so again, no algebra to turn this into the form of 1 over 1 plus, or 1 over 1 minus x, right? So what can we do to this expression to help us out? We just differentiate, right? So notice d by dx of 1 over 1 plus x becomes 1 over 1 plus x, like this, yeah? Which is 1 over 1 minus x, yeah? Which is this power series expansion, the sum k equals 0 to infinity minus x to the k, which is this thing, k equals 0 to infinity of minus 1 to the k, x to the k. So we can take its derivative, and that thing becomes something that we can represent a power series. Now what's the next step? What's the next step? Integrate the power series. So we've differentiated to get into this world of differentiation. We now have a power series. We need to get back. Yeah? So I take the antiderivative of the derivative. we get back to where we started plus a constant c, right? So we'll put the constant c on the other side. And, okay, let me put the constant c here just to be completely correct in everything I write. So, and if we take the antiderivative of this power series, it's an easy thing to do because the power series is completely nice to integrate. We just integrate term by term. So it's the sum k equals 0 to infinity minus 1 to the k, x to the k plus 1 over k plus 1, and now plus another constant c. Yeah? So, what do we have? We have this thing is this thing, and this thing is also this thing. Yeah? So this thing is this thing. So this thing is this thing, right? Because we took the antiderivative of both sides, right? So we have this is this, yeah? And then we took the antiderivative of this thing to get back to where we started, and the antiderivative of this thing is another power series. Yeah? So log of 1 plus x. And now we're not going to forget to put the constant c, but the constant c here, we just add it because, and call it c, because the constant c is just a constant c. Now we're not going to write 2c or whatever. Certainly we're not going to cancel the c, right? Because the c is just a general c. Yeah? So this thing is this thing. Plus constant c. Are you happy with what I mean about the constant c here? Speak up if that doesn't make sense to you. Yeah? Everybody happy? Good. All right, but we can do better because we actually can plug in some values of x to find out what constant c is, right? Because we know the graph of log. We know that when we are at 1, we are at 0. So if x is equal to just 0 here, right? We have log of 1. All this stuff from k equals 0 to infinity, since the power is at least k plus 1, is going to involve a non-trivial power of x. So all that stuff here will vanish when x is equal to 0. So we'll have 0 on the left-hand side is equal to c, therefore c equals 0. So put in x equals 0, and then we have that log of 1 is equal to c, and log of 1 is 0. So c equals 0. So we actually have the power series expansion just neater than that. If the sum k equals 0 to infinity minus 1 to the k, x to the k plus 1 over x plus 1 to the k, and then no constant c. No constant c. Yeah? Cool. All right, so again, I wrote things out somewhat in detail. If I was doing this on my own, what would I do? What would I do? I would just do this. So in one line, I would go log of 1 plus x is the antiderivative of 1 over 1 plus x plus constant c, which is the antiderivative of the sum k equals 0 to infinity minus 1 to the k, x to the k, dx plus constant c, which is equal to the sum k equals 0 to infinity minus 1 to the x, minus 1 to the k, xk plus 1, and I have another c, which I still call c because all c's are the same, plus constant c. So I have this representation, and then I put in x is equal to 0 to kill off the c. So I'm not going to write that again. And then the c just gets killed off by putting x equals 0. So I get this. So in one line, if you just put everything you know all together in one line, you get the answer pretty quickly. And maybe that's easy, maybe that's a better way for you to do it. So don't start to like separate off the stuff. Just take your function, write it as the derivative or the antiderivative of something, put in the power series expansion and keep working it through. Maybe that's a way not to get lost on your sequence of steps. So whatever we did, if it's integration or differentiation, at the last step we have to get back. We have to reverse it. Yeah, we have to reverse it. All right. Example. I don't know the number. Find power series of Arctan. And the power series around 0, I should emphasize. Okay. Arctan of x. Definitely no algebra to turn this into 1 over 1 minus x, right? Okay, so solution. What do we do to get something out of this? How do we start this? We have to integrate or differentiate. What do you want to do with this guy? Yeah, so what is the derivative of this guy? What's the derivative of Arctan? Yep. So that's the guy we want. Yeah. So now we're getting fancy at this, or hopefully. Let's do it in one line. So we differentiate this guy. Yeah. And what do we get? We get 1 over, well, no, let's do it in 2 lines, so several lines. We get this thing, right? Yeah. So if we take the antiderivative of 1 over 1 plus x squared dx, then indeed this thing is arctan of x plus constant c. Yeah? And then 1 over 1 plus x squared, slowly, is 1 over 1 minus x squared. It's the sum, k is equal to 0 to infinity, minus 1. Minus 1 to the k, x to the 2k, like this. Yeah? And therefore, when we take this antiderivative, then we get antiderivative through this expression. Okay, just like this. And this says that this is equal to this. Again, the constant c, we're just going to write it as constant c. So arctan of x is this power series k equals 0 to infinity, minus 1 to the k, x to the 2k plus 1, x to the k plus 1 plus constant c. And we can figure out what constant c is, because again, when x equals 0, arctan is 0. We know the graph of arctan looks like this. Yeah. So this constant c just vanishes. So x equals 0 implies c equals 0. And that's our power series. Yeah, and the radius of convergence is the radius of convergence that lets this work, which is for mod x less than 1. So the function is defined everywhere, right? But we only can represent it over this interval. But over this power interval, we actually can represent it. So we can do many, many nice things with this function so long as we stay within this interval, because we actually have a power series representation. Okay, in one line. So what do we want? We want this guy, arctan. So we know that arctan is the antiderivative of 1 over 1 plus x squared dx with a constant c. So I'm going to put the constant c over here. And then this thing we power series expand. Like this. And then we do the integration through the power series Oops, drop the K. Plus constant C, and that's the same thing we had before, and then again, we just kill the constant C when I'm sticking x equals 0. So you can keep the information all in one line, just like this if you want to. You can break down what you did, making sure you are reversing the steps, right? So we go from this thing, we are taking the antiderivative, so we're integrating. This is how I got this wrong last time. No, we are differentiating. We are differentiating to get 1 over 1 plus x squared. Then we are power series expanding. Yeah. And then we have to reverse the thing we did. So we differentiate, now we integrate to get back. And again, we kill the constant C by sticking x equals 0, right? So we can double check, or triple check that we are doing things right, right? First, we carefully wrote down the stuff we knew, right? Yeah. We know that the derivative of this guy is 1 over 1 plus, well, x squared. Therefore, if we take the antiderivative of this guy, we arctan, right? And we know that this guy, we power series expand, and then we take the antiderivative and we get what we want, right? Here we put it all in one line. Arctan is the antiderivative of 1 over 1 plus x squared. Yeah. Therefore, we'll just put that inside, yeah, and then carry it out. We get the answer. And then now here we check that we did things in a logical sense. We started this guy, we differentiated to get the thing that we wanted, right? We did the power series expand, we integrate. Yeah. So this is just a kind of layout of the steps we did in the first method. Okay, feeling good with this? Yeah? All right, so it takes a little bit of practice, but this isn't particularly hard. I like to do it in this way so I don't get something wrong from one line to the next. Okay, so I have all the information in the same line. But you'll find your own method. Practice this, you'll get good at it. All right, I have office hour now. Stick around if you have any further questions. Otherwise, I will see you on Wednesday. Bye-bye, people.